How about now? Can you hear me now? And I'll just have to do it like this. So you can hear me now, right? It should be okay. Okay, perfect. Yeah, the sound quality must be a little bit worse, but hopefully you can still understand what I'm saying. Right, so I got 8 more questions on circular motion. So we've got plenty of time to talk about circular motion. I'll share my screen. And okay, please let me know if you can't see my screen, otherwise I assume you can. And before we start, please let me know how many problems have you managed to solve for circular motion? How many questions have you managed to do out of 13, I think? Just put a number in the chat, please. 4, okay. There's 16 of you. I do expect a very well, I can last to this. Okay, up to 13. Okay, 5. Yeah, don't be shy. I mean, if it's 0, it's 0. It is you still have 3 weeks left. Okay. All right. Okay, so I can see quite small average. That's all right. And so did you find it very difficult, or you just did not have enough time? So just type in difficult or time. What is the main reason why? Time. Okay. Is there anyone here found it so difficult that just you couldn't? So timing. Okay. 7. Okay. So problem 4. Is that the one with the spiral? Is that the one with the spiral? No. Problem 4 is, yeah, problem 4 is quite tough. Okay, but it's doable. We will do something similar to problem 4 today. Okay. So yeah, just do keep in mind you have 3 more weeks, but these 3 weeks will come quickly. So today we're going to talk about well, we're going to do some very similar problems actually to the ones in the assignment, and hopefully they will help you to understand how to do the problems. So basically we continue what we were doing last week. Okay, so problem 1, a train is traveling along a horizontal curved track. So basically a train is going around a bend with an initial velocity of 54 kilometers per hour, travels a distance of 600 meters with constant acceleration in 30 seconds. The radius of the curve is 1 kilometer. Find the speed and the total acceleration of the train at the end of this section of the track. So we have a curved section of the track. We start from here, we start from A, and we travel to B. So we have the radius of the track is 1,000 meters. Okay, and the train starts, so this is the train starts at 54 kilometers per second. Oh, kilometers per hour, sorry. Kilometers per hour. Can anyone guess why such a number was chosen? Why 54? Why not 55 or 56? What's so good about 54? Anyone? In a way, 9. What's the these are not the usual units that we use. It converts nicely to meters per second, of course. It is 15 meters per second. It's exactly 15 meters per second. You can check that later on. And so train traveling on a horizontal track, 54 kilometers per hour, it travels a distance 600 meters, so 600 meters in 30 seconds. So we can get an average speed. Yeah, so what's the average speed? Average speed, the average, this is V0, initial velocity. No, it's the distance over time. Distance over time. The average speed is 600 divided by 30. So that's 20 meters per second. Now, if the average speed is 20 meters per second, what's the final speed? Now, the answer is very intuitive. But if the initial speed is 15, the average is 20, what's the final speed? $25, of course, 25 meters per second. Okay, I'm leaving this without proof. I mean, you could easily prove it using this formula. S equals V0 plus V1 over 2 multiplied by T. This is one of the Suvat equations. Yeah, so V0 is U, V1 is T, the Suvat. Okay. So the final speed is 25. The initial speed is 15. So the train is accelerating. Okay, that wasn't. Yes, you can model this on a velocity time graph with a constant gradient. Perfect. So yeah. Now so what do we need? So we found the final speed. Then we just need to find the acceleration. And acceleration consists of two parts. First of all, the train is accelerating along the track. The train is accelerating along the track, and this acceleration is called tangential acceleration. Tangential acceleration. But also, the train is accelerating towards the center of the circle, and that's called the normal acceleration, or the centripetal acceleration. I'm just going to call it normal acceleration for now. Acceleration. So a tangential acceleration is the change of speed divided by time. And the normal acceleration is v squared over r. V squared over r. And that's all we need. So tangential acceleration along the track is the change of speed. So change of speed divided by time taken, and we know that we know those. We have change in speed is 10, so it's 25 minus 15, and the time is 30. So this is 1/3 meters per second squared. Okay. Well, technically, you shouldn't leave, in physics, you shouldn't leave answers as fractions, especially when you're given numbers. So it's 0.333 meters per second squared. And the normal acceleration, or the centripetal acceleration, is v squared over r. And we're interested at the acceleration at point B, at the end of the section. So at point B is going to be 25 squared divided by 1,000, and this is 0.625 meters per second squared. And then finally, the acceleration of the train is the total acceleration. So the speed we know, 25, and the acceleration is the square root of a tau squared plus a n squared, which is square root of 0.333 squared plus 0.625 squared, and that should be approximately 0.708, approximately 0.708 meters per second squared. Okay, so I hope that makes sense. Ruben, can other people hear me? So Ruben, it must be. Yes. Okay. Have you tried turning it on and off again? And that's it. Any questions? Any questions about the train? If I wasn't clear, I'm drawing. Yes, exactly. Great show. If I was looking at the train from the top, the picture is the train from the top. Yeah, it's not a train on a hill. View from top. I just want to explain that. View from top, from above. Yeah, so the track looks more like this, and those thingies. Right. That's an excellent that's an excellent question. Don't Suvat equations only work for straight line paths? Look, that is a brilliant question. Thank you for asking that. Let's say a runner runs 2 tracks, and they're both 400 meters long. 400 meters long. 400 meters long. Assuming you Zain, I'll answer your question about acceleration. Acceleration, the tangential acceleration is constant. So the acceleration along the path is constant. So you're starting from here, and let's say you're starting with 0 meters per second, and here you're starting with 0 meters per second, and you are accelerating. Here you're accelerating with 1 meter per second squared, and here you are accelerating with 1 meter per second squared. Now here in the circular path, 1 meter per second squared is constant acceleration, and this is the tangential acceleration. Tangential acceleration is 1 meter per second squared, and here the acceleration is simply 1 meter per second squared. The distance traveled can be found as 1/2 at squared, and here the distance traveled can be found as 1/2 a tau t squared. Of course, as the runner gets faster and faster and faster, you will also have the normal acceleration, which is the centripetal acceleration, which is over r, which will be increasing. Yeah, as you can see, but the tangential acceleration would stay constant. The acceleration along the path will keep constant whether the normal acceleration is not constant. And because acceleration is the square root of tangential plus the normal, it is not constant. But a tau is constant. Does that make sense? And if you run around a track, even though you run around a circular track, you can still use speed as distance over time, the same way as you can use suvat for constant tangential acceleration. It's the same thing as angular acceleration, yes. It's the same thing as angular, well, it's very similar to angular, except angular acceleration is the tangential acceleration divided by the radius. Acceleration is roulette is better. Acceleration is constant. For constant acceleration, for constant tangential acceleration. So it's as if you cut the circular path. You take the circular path and you wrap it around and make it straight, so flatten it out. So this is what we're talking about when we say tangential acceleration. Tangential acceleration is just acceleration along the path. Is that making sense? Okay. Chisholm, why does the centripetal acceleration act towards the center of the circle? Well, there is a proof. There's a proof on page. What page 5? Yeah. So I spent a lot of time drawing this. So please do read it carefully. And yes, so this is the centripetal acceleration. As you can see, this red arrow, this is the acceleration. This is the change in velocity. Is pointing towards the center of the circle. So yes. Okay. Does the acceleration remain constant going up the hill? We are not going uphill. Yeah, just to be clear, the train is not going uphill. The train is making a turn, but it is accelerating. So the acceleration along the path of the train. So if you're the train driver, your speedometer shows constant acceleration. Yeah. Your speedometer does not show that you're turning. You need an accelerometer for that, because the speedometer only registers the change in speed and time, and change in speed over time is the tangential acceleration, not change in velocity over time. Yeah, so you see the difference. Tangential acceleration in this particular scenario is the change of speed over time, whereas the normal acceleration is v squared over r. It's to do with the change in direction. So acceleration caused by changing direction, or rather changing direction caused by acceleration. Yeah, putting the horse before the carriage here. But yes, velocity, no. When I say tangential acceleration, I say change of speed over time. When I say acceleration, it's change in velocity over time, which is just total acceleration. It's change of velocity over time. Okay. Right. Problem 2, which is very, very similar to one of the problems. Linear velocity of points at an edge of a spinning disk is 3 meters per second, and points 10 centimeters closer to the axle is 2 meters per second. Oh, meters per second. Okay. That's fine. I just made a mistake. Just found a mistake I made. Anyways, so you have points. You have a point here at the edge, which is rotating at 3 meters per second. That's v1, 3 meters per second, and 10 centimeters away. So here, so 10 centimeters. It is rotating at 2 meters per second. 2 meters per second. Now, the beautiful thing is you can solve this problem geometrically. If you take the center of the circle, if you draw a line, it should pass like this. And you can use geometry to find that, because any velocity will match this. So that's how it works. But let's do it properly. So we'll call this R1. This is, oh, sorry, R2. And we'll call this R1, or yeah, R1. And we know that the angular velocity is constant, is the same for all points on a disk. So this is constant. So, and omega R1 is equal to V1, and omega R2 is equal to V2. We divide them, and we get R1 over R2 is equal to V1 over V2. Okay, and we can get that R1 is, sorry, that's V1 and V2. V1 and V2. V1 and V2, so it's 3 over 2. Or in other words, R1 is equal to, so from here, R1 is 3 over 2 R2. We also know that the difference between R1 and R2, so R1 minus R2 is 10 centimeters, is 10 centimeters. So we get 3 over 2 R2 minus R2 is equal to 10. R2 So 3 over 2, that's half R2. R2 is 20 centimeters. And R1 similarly is 30 centimeters. And what are they asking? They're asking about the frequency, angular velocity, and the time period. Okay, so we can work that out. So first we'll start with the angular velocity. Angular velocity, as we know from this formula, is V1 divided by R1. V1 divided by R1. Omega is the angular velocity, yes. So V1 is 3 meters per second. So it's 300 centimeters per second over R1, which is 30 centimeters, which is 10 radians per second. 10 radians per second. And then we need the time period. The time period is 2 pi divided by omega. So it's 2 pi divided by 10. So 0.628 seconds. And finally, frequency is the reciprocal of that, is omega divided by 2 pi. And that is omega is 10 divided by 6.28, which is 1.59, and that's hertz. All right. Any questions here? So this is pretty much problem. Don't remember which one. What is one of the problems? Yeah. Problem 3. Okay. Problem 3. Due to Earth rotation, the same mass on the equator and the poles will weigh differently. I'm putting weigh in quotation marks because weight is the gravitational force. It's not really different. What is that? What is that difference? And what would the length of day need to be so that we would be weightless on the equator? Assume the Earth is a perfect sphere. Yeah, so there is a difference because of the Earth's rotation, the Earth is a bit squashed at the poles, so it's a bit wider on the equator. But we are not going to take that into account. We just simply account for the Earth's rotation. Yes, exactly. That's why I am putting in quotation marks, because it is not correct to say weight, they will weigh different. But when we say weigh, we mean we put it on scales and we see a different reading, right? A weight is the force of gravity, but when you put something on scales, you don't measure the force of gravity. You're measuring, which force are you measuring when you stand on scales? The normal reaction, of course. Yeah, you're measuring the normal reaction, not the weight. Even though we say we weigh the object, because we assume that the normal reaction and the weight are the same thing, which are sometimes not. And if you ever tried riding on an elevator, standing on the scales, you will see that it's going to change. Yeah, do this experiment if you have scales. Get on an elevator, on a lift. Sorry, get on a lift and press some buttons, and you see how the readings change when the lift starts and stops. Quite an interesting thing. Or if you're lazy, just find a video. Or if you don't have an access to a lift, find a video on YouTube. They're quite interesting. And right, but what's going on here? So let's draw a picture. So this is the planet Earth, and we are looking at it from the North Pole. So this is the North Pole. And which way is it spinning? Clockwise or anti-clockwise? Where does the sun set? Clockwise or anti-clockwise? You can shout out using your mic. We're looking from the top, and the Earth is either going that way or going that way. So which way is it going? On. Where does the sun rise, and why does it rise there? The sun rises in the east. So what does that mean? Yes. So what does that mean? How anti-clockwise? Yes, Harvey. It is anti-clockwise, of course, because the sun is here, and if you're standing on the planet, in order for the sun to rise in the east, the planet has to go that way. So the sun is here, and you are right. Okay. Right, now let's look at the forces acting on a person standing on the equator. So the Earth is rotating anti-clockwise. A person is standing on the equator. And there are two forces acting. There is the weight force, and the normal reaction force. mg, and normal reaction. Are these forces balanced? Are these forces balanced? Tycho, can you say why? Can you use the mic and say why? Ooh, RKS. Good one. Not with rotation, of course. It is rotating. It is rotating, and if it's rotating, that means it is accelerating, always. There is an acceleration, and it's downwards. So the forces are not balanced. The NMG are balanced, but the rotation isn't. No, Tycho, they are not balanced, because you are accelerating towards the center of the planet because you are rotating. If you're rotating, you have a centripetal acceleration, which is equal to v squared over r, or, as I prefer, omega squared r. Right, you are accelerating. So writing the Newton's second law, it is you're accelerating downwards. So mass times acceleration is equal to the resultant force, so mg, minus n. And we know that ma, and that am omega squared r is equal to mg minus n. FMA, yes. And then the normal acceleration is equal to mg minus m omega squared r. And this is the beauty of it. When you are standing on the equator, you're not measuring mg, you're measuring mg minus that thing. You're not measuring mg, you're measuring mg minus this. Let's get some numbers. So we know omega is 2 pi divided by the time period. How many seconds in a day without a calculator? $86,400. Well done. All right. 86,400. And it is 7.27 times 10 to the minus 5 radians per second. Radians per second. So that's quite a small angular velocity, as you can imagine. As you can imagine. So we can see that the normal reaction mg minus that. So what can we say? Well, I don't know if we should put it put some numbers here, but let's okay, let's put some numbers. So for a 70 kilogram person on the pole, n is simply mg, because radius is 0. The radius of the circle is 0, and therefore it's equal to mg. So that's 70 times 9.81, which is 70 times 9.81 is 686.7. 686.7 newtons. And on the equator, n is mg minus m omega squared r, which is 70 times 9.81 minus 70 times omega 7.27 times 10 to the minus 5 squared, multiplied by the radius of the planet, and the radius of the planet is 6,400,000, 6,400,000 meters, and that is, if you do the calculation, minus 70 times 7.27. Oh, you need a square, 7.27. And 10 to the minus 3 squared multiplied by 6,400,000. 686.7. 684.3. So not a dramatic difference, as you can see. So minus 686.7 divided by 686.7, which is 0.34% difference. So not a massive difference. So 0.34% difference. Okay. It's not like the central bank. It's not like the Bank of England today decided to increase the percent rate by 0.5%. And everyone's mortgages went up by £200-300. So this is not that situation, because 0.5 with a mortgage you have to pay basically it adds up. So 0.5%, an additional 0.5%, that's an additional 0.5% of your house that you have to pay every year. So if you take a 0.5% of an average house, 0.5, and an average house in England is 250,000, 725, 0.005, it's £1,000 per £1,000 per year, which is divided by 12. It's 100 on average. The average house in the UK today became £100 per month more expensive. Just for you to understand what that 0.5% means. It will change. Not necessarily for the better, but it will change. Anyways, 0.34% difference. So that's not a massive difference. But what if the Earth was spinning faster? What if the Earth was spinning faster, and it was spinning so fast that you were feeling weightless? Now, when astronauts say that they feel weightless, they're not actually weightless. What they are experiencing is that they don't have any normal reaction force. And that is the feeling that they call weightlessness, which is not actually weightlessness, it's normal reactionlessness. We don't like saying normal reactionlessness, so we say weightlessness. But weightless means n equals 0. Weightless means n equals 0. Can you think of a situation where you, as an individual, have felt weightless? Tycho, I'm sure you have experienced it many times in your life. Not a lift, unless you were on a lift that crashed. On a roller coaster, very close. On a roller coaster, you get falling. Yes. Trampoline. Yes. When you dive, absolutely. I was thinking of a dive. Yes. Diving off a cliff. Have you jumped off a cliff, Tycho? Well, actually, as a matter of fact, I have. I did cliff diving. Not because I'm so sporty, but out of teenage stupidity. But anyways. Yes, when you jump off a cliff, or you simply jump off a chair, the feeling that you get is weightlessness or normal reactionlessness. So whenever n is 0, you are weightless. I say weightless because it's not true weightless. True weightlessness would be exactly the same. You would not feel any different if you were in the middle of the universe with no gravity. You would not feel different from jumping off a chair. Okay, it's just for a longer time. And there's the small matter of not being able to breathe. Yes, equivalence principle. Right, sorry, I'm just having issues with the board. Okay, I hope that means, I hope this means n equals 0. Oh no. Principle. I didn't notice, so that's fine. Okay. Maybe, what can we do here? Maybe just my room. Temporarily, my room. Okay. Could objects orbit from certain conditions? A pencil case will orbit around your bag if you are in a away from any planets. Okay. So where were we? So I was saying, okay. So normal reaction in that case. Normal reaction. Normal reaction. Normal reaction is sorry, it's not the board I normally use. It's mg minus m omega squared r, and this is equal to 0, and that means mg is equal to m omega squared r. Cancel the m's, so omega squared is equal to g over r, and so omega is square root of g over r, and then our time period is 2 pi divided by omega, which is 2 pi square root of r over g. A formula that looks awfully familiar. So the question was, how fast does the Earth need to spin? What is the omega for the Earth, for the planet, in order for you to feel weightless when you're standing on the equator? Well, you won't be able to stand, you would float above the equator. It is almost exactly the same thing as the equation for a pendulum, and this is not a coincidence. Another non-coincidence, if we actually try to evaluate this, so 2 pi square root of r, which is 6,400. Please do remember this value. 6,400 kilometers. This is the radius of the planet divided by g, 9.81, and you get a value which is I have it here. 5,074 seconds. 5,074 seconds, which is 85 minutes, approximately, which is approximately 85 minutes. I'll double check that. 5,074 divided by 60. 84, well, 84.6, yeah, 84.6 minutes, 85 minutes. Now, that kind of reminds me of something. What else is very close to 85 minutes? Is something related to our planet? Does anyone know? Oh, it is 84.6, but I'm rounding. 84.6. Okay, I'll do 84.6 minutes, which is 1 hour 25 minutes. Length of a film. Yes, you're on the equator, you feel weightless, and you are watching a movie. No, the orbital time, International Space Station. It's 90 to 93 minutes. That's not a coincidence, because the International Space Station goes around the planet, so ISS orbital time 90 to 93 minutes. It's not a coincidence, because what it is actually feeling weightless, and is going around the planet, and is going just fast enough to feel weightless. Okay, right. So I'll copy that. So hopefully, right. The station itself experiences no normal reaction force. When you're standing on the surface of the planet, you have the normal reaction force, and you have the mg. Normal reaction force is the force with which the ground is pushing you upwards. Yes, because the radius of the planet is 6,400 kilometers, and the radius of the ISS is 6,800 kilometers. So it's 400 kilometers above the surface. So 400 kilometers, and that's the extra radius. So it's just going slightly above. All right. Ever so slightly. If you really think about it, 400 kilometers. That's so on the weekend I went to Wales, and that was 400 kilometers. So not Wales. All right. And so I could have driven to the International Space Station in 4 hours. Right. Apologies. Something's going wrong here. Let's see if I can reload that. Okay. Well, the next question was explain the same phenomena, but from the point of view of if you are looking at an non-inertial frame of reference. So I've spoken about non-inertial frames of reference last session. Non-inertial frame of reference, and in this how do I change the color? Let's make it non-inertial frame of reference. A non-inertial frame of reference is an accelerating frame of reference. And in the previous session, 2 weeks ago, I was explaining how laws of physics do not work in non-inertial frames of reference, or they don't work in the way they normally do. Yeah, non-inertial frame of reference. So the planet is a non-inertial frame of reference because it's rotating, and because it's rotating, it's accelerating. So everything on the surface is accelerating, therefore it is a non-inertial frame of reference. And we were talking about the existence of force, which is called centrifugal force. Centrifugal force is an imaginary force. Imaginary force equal to minus centripetal, the centripetal force. The centrifugal force, centripetal, is minus the centripetal force. Do not mention in A-levels exams. Please do not mention centrifugal force in A-level exams. But you are standing on the surface of a planet. Oh, this board is surprisingly convenient. You're standing on the surface of the planet. This is a non-inertial frame of reference, and you experience. So you're standing still. We are in your frame of reference, and you experience a force. You experience gravity. No, sorry, this is not convenient. Okay, you experience gravity, mg. You experience normal reaction, and also you experience a force, an upwards force, which is the centrifugal force, F centrifugal force, which is m omega squared r. By definition, because that's what centrifugal force is, minus the centripetal force, so it has an upwards direction. So if you're sitting on the planet and the planet is rotating, you think that the planet is trying to throw you off. Yes, like in a merry-go-round. If you're on a very fast merry-go-round, you feel that the merry-go-round is trying to throw you out. Yeah. We've discussed 2 weeks ago why this is not true. It's your body's tendency to travel in a straight line. But once you are in your frame of reference and you close your eyes, you have this sensation that something is trying to throw you off. And we call this centrifugal force, but it is an imaginary force. It only exists in a non-inertial frame of reference. But since you are in a non-inertial frame of reference, which is a spinning planet, that means you kind of experience that force. And what we can write here, that these forces have to be balanced because you are stationary. In your frame of reference, you are stationary. And we have mg in your frame of reference you are stationary. You are stationary, therefore the forces are balanced. So mg is equal to n plus m omega squared r. And from here we get n is equal to mg minus m omega squared r, which is exactly the same result as we had before. Okay. How well do you understand this method? Please please put a number in the chat on a scale of 1 to 10. about 8. So you are in your frame of reference, and you experience 3 forces, mg, n, and but this is imaginary. So please do not never ever use that in an exam. Never use this method in an exam. They will try to destroy you just because you use this method. Okay. Look, this force only exists if you place yourself in a non-inertial frame of reference. But Newton's laws do not work in non-inertial frames of reference. Therefore, you cannot. It's a mathematical adaptation which leads to the correct answer, but it's not a physical thing. There's no physical force pushing you out. It doesn't exist. If that makes sense. I was talking quite a lot about this 2 weeks ago. So the problem is that if you let's say you are in a car and you're making a sharp left turn. So you're in a car and the car is making a sharp left turn. You feel as if you're being pushed to the right. Well, at least that's your sensation, that your body is being squashed into the right-hand side of the car. So this is a view from the top. So these are the wheels of the car. There's a spoiler, obviously. Okay, headlamps. So if you were traveling around a stationary Earth, you'd have extra downforce. Not extra downwards force. No. Well, yeah. If you were standing on a stationary Earth, yes, you would feel heavier. You would feel a little bit heavier, like 0.3% heavier. Yes. But when you are in a car, and this is your body, and just like this is you, yeah, this is you. So what forces do you feel? Well, you only feel a force towards the center of the centripetal force, and that force is the normal reaction from the seat, is pushing you towards the center. Because if there was no centripetal force, you would continue traveling in a straight line. You would continue traveling in a straight line. The centripetal force is the force that causes you to travel in a curved path. Centripetal, if with no centripetal force, you would travel in a straight line. Fc causes your body to turn. And this is physics. No, we're talking about your body. So it's the normal reaction from the seat. From the point of view of the car, yes, of course, it's the friction. Hopefully your body does not touch the road. It's not pleasant. I've fallen off bicycles to tell you friction against the road is not pleasant. Groceries move. Well, do they actually move to the sound? Look, let's say you had a grocery bag and it was here. This is your grocery bag. And you say, oh, the grocery bag has shifted to the right. Has it, though? Your car after making a left turn, your car is here, and the grocery bag is here. Has it actually moved to the right? Relative to the car, yes, but relative to the road, no. Relative to the road, it has moved to the left, if anything. What the bag was trying to do, the bag was trying to travel in a straight line. The bag was trying to travel in a straight line, but the friction and the normal reaction force did not allow it to. Your groceries go to the right relative to the car, but not relative to the road. So the force on the groceries is to the left. There's no force to the right. Okay. Does that make sense? So the centripetal force is a real force. And it causes you, your groceries, and the car to turn left. But then somebody comes in who didn't do physics in school, and they say, oh, there's a centrifugal force pushing you outwards. Okay, so either they didn't do physics in school or they did physics at university. Because if you do physics in school, you are taught that there's no such thing as centrifugal force. And then at university in year 2, they tell you, well, actually, there is such a thing as centrifugal force, but it's an imaginary force. It only exists in your imagination, in your frame of reference. Sorry, not your imagination, of course, in your frame of reference. And that is the frame of reference in the car. And in that frame of reference, your groceries shift to the right. And the force that caused them to shift is called centrifugal force. Centrifugal force caused shifting of your groceries, but only if you assume that you are stationary. You are thinking that your car is stationary and there's a magic force that suddenly caused your groceries to shift. Nothing's pushing the groceries. They just suddenly decided to shift. And that's why we call it an imaginary force, because it doesn't really exist. Because it doesn't, it's a mathematical way. So this is pure maths. This is not a physical force. It's a mathematical force, which is convenient because it gives you the correct answers, but it's not a real force. Yes, the centripetal force is the real thing, is the real stuff, and the centrifugal force is just a mathematical model. Helpful one, but not. Yes, so please don't mention that. So that was problem 4. Repeat problem 3, working in a non-inertial frame of reference. That's what I was trying to tell you. What I'll do is I will, before I forget, I will. No, I thought I'd like that, but no, I don't. I don't like this whiteboard. Okay. Right, so we've got 20 minutes, and I'm just thinking which question would be more important. A small piece of mud gets detached. You know what? I'll do this one, and then I will just skim through the other ones. A small piece of mud gets detached from a wheel which is rolling while slipping with speed v. So this the wheel's speed rolling. The radius of the wheel is r. What height will the piece of mud reach if it detaches at point A? So at point A, we know that the piece of mud has two velocities. First velocity is the tangential one. This is caused by the rotation of the wheel. And then there is the horizontal force, this horizontal speed, which is this one. Okay, so this was here. You had so in the frame of reference, yes, that's convenient to see. So in the frame of reference of the wheel, this is the speed of the point A in the frame of reference of the wheel, v1, and this is just v, the speed of the wheel. Okay, hope that makes sense. So this is very similar to problem to example. Sorry, not problem. The example. Example 2. You have the speed of parts of the wheel in the frame of reference of the wheel, and you have the and then you add the speed of the wheel. So at this point, you have v1, then you have v, and obviously they are the same. They are they're equal vectors because it's rolling without slipping. And then you need to find this angle. Now this angle is going to be alpha. Yeah, without I trust you can figure that out, why this is so, because this is 90 degrees. Just using geometry, this is easy to show that this is alpha. And this is a triangle. This is an equilateral triangle because this side is equal to this side. They're both equal to v. And this is the true speed. This is the initial speed of A, u. So u as a vector is v1 plus v. Okay, so u is the initial velocity of the mud. Okay, does it make sense so far? On a scale of 1 to 10, please. Does it make sense? So v1 is the speed because of the rotation, and v is the speed because the wheel is turning, and the total speed is u. Total speed is u. Oh, because if a wheel is rotating, if the wheel is rolling without spinning, the speeds they have to match, don't they? If a wheel is rolling at, I don't know, 10 meters per second, 10 meters per second, this would be also 10 meters per second. So in the frame of reference of the wheel, all parts of the wheel travel at 10 meters per second in the frame of reference of the wheel. 10, 10, 10, 10. I hope that makes sense. So if this is 10, then this is also 10. So if this is v, this is also v. So I'll rub that out. It's not 10, but it is. Right. And here we're going to use a cosine rule. Yes, cosine rule can be used in physics. Cosine rule. Sine rule. You have u squared is equal to v squared plus v squared, so 2v squared minus 2 times v times cos, so 2v squared cos alpha. So u squared is 2v squared, 1 minus cos alpha. All right, that's the initial speed of the piece of mud. Okay, so the piece of mud starts with velocity u, and then its projectile motion. Projectile motion. Oh, wow. It's slightly harder than I thought, but yeah, so I messed up slightly. But anyways, we need to find the maximum height, h max, maximum height. And well, we know we need to find the angle. We need to find this angle, theta. This is theta, and we're going to use just geometry, just pure geometry. So I'm gonna use, in the frame of reference of the ball, it would be stationary. So why would its velocity in the ground frame of reference be important? In the frame of reference of the ball, I see what you mean. RKS. I think I know what you mean. So the two, you're asking why the two velocities have to be the same. Well, they have to be the same because the bottom part of the wheel is stationary. This point on the wheel is stationary. Therefore, this velocity has to match the tangential velocity, if that makes sense. I just realized one thing, because it's not slipping. If the wheel moves 10 meters, then 10 meters of wheel have touched the ground at that time. Yes, that's a brilliant explanation. Thank you. That's much better than what I'm trying to achieve. I just realized one thing, which I've overcomplicated this solution so much that we don't need to go that far. We don't actually need the this diagram. I mean, okay, we'll leave this diagram just for the sake of it. But what we need to understand that the horizontal velocity does not matter. The horizontal velocity has no effect on the height at which for the height reached by the piece of mud. Therefore, I only need the vertical velocity. So y is the vertical velocity. It's going to be v multiplied by sine alpha. So simple. Okay. Sorry, something's wrong with my Estonian whiteboard. Okay, so you have a wheel. You have a wheel and it's spinning. Sorry. You have a point on the wheel and it has velocity like this, v. And because we know that this angle is alpha, this angle is alpha, we can safely say that this angle is alpha. This angle is pi over 2 minus alpha. Therefore, this angle is also alpha, because this is a right angle triangle. So we can split the V into two components, the vertical component and the horizontal component. We don't care about the horizontal component. We only need the vertical component. So U, Y, the vertical component, is V sine alpha, V sine alpha, and that is important. Now, we also need to, because we need the maximum height, H max, but to do this, we need the initial height as well. Initial height is the initial height plus, and now how far do you go? If you're launched with this speed, V sine alpha, if you're launched with V sine alpha, you can use conservation of energy. So kinetic energy is equal to mgh. So kinetic energy is 1/2 m v squared sine squared alpha equals mgh. So plus h. H is the height, is the extra height. And from here you cancel m. You have h is equal to v squared sine squared alpha divided by 2g. Okay, that's fine. And h0, h0, you need h0 as well. H0 is the initial point of launch, h0. And it is slightly above the ground, so that's r minus r cos alpha. Okay, so H max is r minus r cos alpha plus v squared sine squared alpha over 2g. Okay, then what would cover 10 meters of centripetal distance? Not sure what you mean. Oh yes, I see what you mean. You mean circumference, 10 meters of circumference. Okay, and that's the maximum height. Are we given the radius in that question? I don't think so. No, we're not given the radius. And r minus r cos alpha plus v squared sine squared alpha divided by 2g. Oh, H max, sorry. Oh, okay. H max is equal to I see, r 1 minus cos alpha plus v squared. So sine squared out v squared over 2g, and this can be written as 1 minus cos squared alpha. And so 1 minus cos alpha r plus v squared over 2g 1 plus cos alpha ish. Okay, let's go to Desmos and just try to plot that. So h equals, okay, we don't use hy, is equal to 1 minus cos x, 1 minus cos x, and then a constant. Well, we don't know the radius, but we can put some sort of radius, 3 plus v squared over 2g. Well, we don't know that, but anyway, it's going to be I'll just experiment for now. 1 plus cos x, and interestingly, does anything changes if I change this number? Okay, so what happens is we have a maximum, we have a peak value, and we have a minimum value, and the minimum value is when it's pi, and that's obvious. So what that means, that if you have pi, when the angle is pi, that means you are at the top. If you release it from the top, it will yeah, you can, of course. If you release it from the top, it won't reach more than the double radius, and double radius is 6 in this case. So it makes perfect sense that pi and 6 are here. And here, this peak, this is the maximum. So somewhere between 0 and pi, so 0 is the bottom and the top of the wheel, this is a maximum value. And it's in fact 1.955. 1.955 radians. So that's 1.955. That is divided by pi and multiplied by 180. That's 112 degrees. 112 degrees. So here. So what this means, when alpha equals pi, so when that means you are reaching from the top, the v, so it's released from the top point. When alpha equals pi, the maximum height h max is equal to 2r, because this is r, this is 2r, because you won't go higher than the top of the wheel, obviously. And here, so you have maximum h is max when alpha is approximately 112 degrees. So if the piece of mud detaches from the wheel when alpha is 112 degrees, you will have maximum height. Yeah. Okay. So hopefully that's that. Right. I do want to go through the spiral one. I know the spiral was very difficult. So what you need to understand here, let's take a piece of this spiral. So I'm going to go about 15 minutes over time. If you do need to go, by all means, but I do want to do this. Let's look at this piece of spiral, Okay. And we're going to unwrap it. We're going to unwrap it. And so this piece becomes like this. Let's say we make it straight. And the length of this piece is L. H0 is the initial height. Is where is the point of release. This is going to be H. And the bottom part, somebody help me, please. What's the length here? Two pi r. It's going to be 2 pi r, where r is the radius. And your angle alpha is here. Okay. Now, in the question that you have, the car is going at a constant speed. So when you look from the top, you will see this. And to find the centripetal, to find the acceleration, you simply need omega squared r. Omega squared r, where r is the radius of the circle, and omega is the angular speed. So that's all you need to do. So it's quite an easy problem. You just need to figure out what omega is. Okay, that's for your problem. Now for this one, it's slightly harder because it is accelerating. So the ball is accelerating downwards along the slope. So that's the tangential acceleration. And also it's accelerating towards the center. So A tangential is, in this case, it is G sine alpha. And the normal acceleration is going to be V squared over R, but not V squared, because we are moving down the slope. Not all, we need the speed, how fast it goes around the circle. So it's going to be V squared cos squared alpha, like this. V squared cos squared alpha. And then you find V squared. You know, use conservation of energy to find V squared. Okay, so I hope that makes sense. We will have, yes, hope that makes sense. So acceleration, to solve this problem, you need to flatten. Well, because it's, look, you need the speed along this line, not along this line. So that's why it's cos. So the speed is V cos alpha, but it's squared. It's the speed along this one. You need to flatten the spiral. The spiral. You need to flatten the spiral. Okay, problem 7 and problem 8. We don't have time to do problem 8, definitely. It's quite a difficult one. It's fun to do. So if you have time, do it. But problem 7. And this is a really fun one, because this is what happens when you go to university and you start studying physics. They ask you a simple question: what is the kinetic energy of a hula hoop? And you say it's mv squared over 2, which is obviously incorrect. And your university tutors go, ha ha ha. How on earth do you think that a rolling hula hoop has kinetic energy 1/2 mv squared? So can somebody tell me why it is not 1/2 mv squared? Oh, what do you mean it's not linear? No, we're just talking about a hula hoop. So forget question B. Forget question B. Forget the picture. We're talking about a hula hoop rolling along a horizontal road, horizontal floor, and with speed v. And it has mass m, speed v, and the kinetic energy is not 1/2 mv squared. And I think we got the right answer, Ruben. Bottom of the hoop is traveling a different speed to the top. Yeah, true, and that's one of the reasons, obviously. But it is because it is rotating. So we have the kinetic energy of translational kinetic energy. That's the kinetic energy of the whole thing moving, plus the kinetic energy of rotation. So to understand this, we need to go into the hula hoop, and we see that all the parts of the hula hoop. So you are in the frame of reference of the hula hoop, and you can see that all parts are moving with speed v. And the kinetic energy of rotation is 1/2 mv squared. And the translational kinetic energy, surprise, surprise, is 1/2 mv squared. So what's the kinetic energy? mv squared, yes. The kinetic energy of a hula hoop is mv squared. That is quite cool. So when solving the problem about a hula hoop, you have to take that into account. So when you do conservation of kinetic energy, you have to say mgh is equal to kinetic energy, which is mv squared. So this is not the same what you're used to. Not 1/2 mv squared. And then they ask you what's the kinetic energy of the rolling wheel, and you say mv squared, and they say ha ha ha, it is not, because it is not. So a rolling wheel is different from a hula hoop because the wheel has a different distribution of mass. And it gets very interesting. It gets really exciting when you see that a wheel and a hula hoop will roll down a slope with different speeds, even though all your life you've been taught that things go down the slope at the same speed, but only if they're sliding. But if they're rolling, it's a completely different story. And that's a whole exciting chapter that you will learn about at university. And sometimes you do that in school. I think Pre-U does that in the Pre-U program. I don't know if it still exists. I used to teach Pre-U. They have a little bit on that. So, but it is quite quite exciting. Velocity rotation with different velocity of travel, though, of course. And that, so we are talking about a hula hoop rolling without slipping. When we say rolling, we usually means without slipping. If it is slipping, then of course you have to add them separately. It's going to be 1/2 mv1 squared plus 1/2 mv2 squared, and it's going to be a different answer. Anyways, so I hope that makes sense. I hope that was enjoyable and informative. And I'll see you next week. Actually, next week it might be David Vaccaro again. We'll see how it goes. But see you soon. Right. You're welcome. See you.